Well, thanks everyone for joining us in person for the presentation of Daphné Lemasquerier. So Daphné joined us in January, where she's working with me on the ocean dynamics, icy ocean worlds. And today she's going to be talking about some of her PhD work on the atmosphere of Jupiter and the dynamics of the environment. And prior to joining us, she did her PhD at Aix-Marseille as part of a fluid dynamics lab there at Europa, which we just about. And prior to that, she did her undergraduate studies at ENS de Lyon, also in France. And she's done a lot of really exciting work that you'll be able to hear about today. And she's received numerous awards and fellowships for that work, including the L'Oreal UNESCO Prize for Women in Science Young Talents French program. And then she's also sought after presenter, and I'm really excited for her to share her work on Jupiter's atmosphere with us today.
Thank you very much, Krista. Thank you for the introduction. So yeah, today I joined the lab recently, so I wanted to give an overview of my PhD work that I did, as Krista said, in Marseille regarding the dynamics of Jupiter's atmosphere. And I also wanted to take the opportunity to present a little bit my postdoctoral project here with Krista, which is focused on the dynamics of Europa's ocean. So that's why I just said Jovian system, but basically Jupiter and Europa. So let me first try to advance the slide. So let me first briefly introduce to you the Jovian system, starting with Jupiter. So Jupiter is a huge planet. It's a gas giant planet. You can see here a footage of this planet taken by the Hubble telescope. It's a planet which is about 10 times larger than the Earth. And you can see that it really exhibits a very interesting multi-scale dynamics at its surface. Okay, now if you take a look at this footage, which was taken by the Cassini spacecraft of the atmosphere of Jupiter, you see in particular that you have very large-scale features, including large-scale vortices, which you see as bright ovals, and of course the famous red spot. And you also have very large-scale winds, which are called zonal winds or zonal jets, and which are responsible for the bandit appearance of Jupiter. It still shows it. So that's kind of the picture of what we see on the surface in the cloud layer of Jupiter. Now we also have some knowledge about how is Jupiter interior composed. So it's a gas giant, so it's mainly helium and hydrogen. But basically what we see is the weather layer where helium and hydrogen are gases. In this weather layer, you have clouds of ammonia, ammonium hydrosulfide, and water. And this is why we see these very beautiful colors at the surface of Jupiter. But below that layer, we know that the hydrogen is then going to become liquid because of the increasing pressure and temperature. Then it's going even to become metallic. And there is presumably a diluted core present in the center of Jupiter. So the two very important points that I want you to remind from here is that it's a completely fluid planet. There are no sharp boundaries at all between any of these layers. So that's very different from what we're used to with Earth's atmosphere or Earth's ocean. Completely fluid. And the second important point is that what you see here, and based from visible observation, is really a superficial picture of what's happening. And so one of the big questions is to understand how all of these features, the vortices and the jets, extend inside of Jupiter's interior. That's not where it comes from. So at the end of the talk, I will be talking about one of Jupiter's moons, Europa. So here I represented the satellites Io, Europa, Ganymede, and Callisto. So when you look at these satellites, contrary to Jupiter, you may say, oh, there's not a lot of fluid dynamics going on, right? Because we see just a solid surface. But we know from the induced magnetic field around Europa that, in fact, there is presumably a salty ocean present below the ice crust that covers the moon of Europa. So this means that there's also some interesting fluid dynamics that needs to be understood and modeled inside of this ocean. But then the challenge is that we don't have direct observations of the motion inside of that ocean. So that's going to be the last part of my talk. So I've listed here just some key questions. I'm not going to address all of them. It's just to give a big picture of the fluid dynamics question that we have regarding these flows, these planetary flows. So for Jupiter vortices, for instance, it's not well understood at all how do they form and why they are so long-lived through time. How do they couple with the large-scale zonal jets? And what is their depth inside of Jupiter? For the zonal winds of Jupiter, again, same picture, it's still not well understood what is the dominant mechanism that leads to the development of these winds. What factor is going to control their final intensity on scale, and why they're so stable through time, because they're extremely stable features in the atmosphere of Jupiter. And finally, regarding Europa's ocean, we're going to ask what drives the circulation in this ocean, what the resulting circulation looks like, and in particular, how the circulation transports heat and materials up to the ice. So to tackle this kind of planetary fluid dynamics questions, we have a lot of different approaches that you can use. Of course, we can use direct observations and try to do inverse problems to retrieve some information. In particular, in the Jovian system, it's very interesting now because we have the Juno mission, which is in orbit around Jupiter since 2016. And we are going to have the Europa Clipper and JUICE missions. So we were really going to have a wealth of observation, direct observations for these systems. Second approach is that you can try to perform a global scale modeling of the whole planetary fluid layer. We try to incorporate as much physics as possible. So that's interesting, but then it's very costly from the computational point of view. And the last approach is that you can say, okay, I'm going to isolate some key processes and try to replicate them and understand them from really idealized theoretical, experimental, or numerical studies, really idealized and focused on key phenomena. So for Jupiter's dynamics, that's the last approach that I used during my PhD that I'm going to present. And for the dynamics of Iceland's ocean, I'm going to present you a global scale modeling approach that I'm currently with Krista. And of course, before going into the core of the presentation, I just wanted to say that we really want to have this idealized approach such that the results that we have are kind of generic, and you could think of applying them to other planetary fluid layers, such as Saturn's atmosphere, Earth's atmosphere, Earth oceans, where you also have zonal jets, or even the external cores of terrestrial planets, where you have the same physical effects that are present. So, simple outline. First, I'm going to show you some work I did in Marseille regarding the depth of mid-latitude vortices on Jupiter. Then I'm going to present you a laboratory model of Jupiter's zonal winds. And I'm going to finish with presenting my postdoctoral project here regarding Europa's circulation. So let us start with the depth of mid-latitude Jovian vortices. So those vortices are mostly anti-cyclones. The results I'm going to present are the result of previous studies and a lot of collaborations, including with Giulio Facchini, who was a postdoc who finished his PhD when I started at IRC, who is now in Brussels. Benjamin Favi and Michael Lebars were my PhD supervisors in Marseille. I also worked with Patrice Legal, who's in Marseille Lab 2. And it was started before with Pedram Hasanzadeh, who's at Rice University, and Phil Marcus with at UTIG. So the question of the depth of Jupiter's vortices arises because, as I said before, we don't really have, at least up to recently, we had no direct measurements of the vertical structure of these vortices. So for instance, Hyde proposed a while ago that, well, the great red spot could be a Taylor column extending deep into Jupiter up to an hypothetical solid surface. So now we know that there's no such surface at depth. And we rather model the vortices that we see on Jupiter as floating structure, which are floating in the weakly stratified weather layer of Jupiter, really floating vortices. However, up to recently, we could not verify directly this kind of hypothesis. And so what we propose, and that's an idea from Michael Lebars, my supervisor, is that, well, you could make an analogy with similar structures that exist within our oceans and which are called the MEDIs. So MEDIs means Mediterranean eddies. So basically, these medleys originate when from the Mediterranean Sea water that outflows through the Strait of Gibraltar. So it's warmer and saltier than the Atlantic Ocean. And it detaches at an isodensity level to form a pocket of warm and salty fluid that is going to rotate in the anti-cyclonic direction. That's called the medley, and then it floats in the Atlantic Ocean and evolves over a very long time scale. And you can see from these measurements of temperature and salinity that they are very compact vortices, and they are also very flat structures. Here, their width is about 100 times larger than their thickness. And so the idea is that, okay, maybe these structures are analogous to what we see on Jupiter because we have the same physical ingredients involved. And maybe we can try to predict what is the shape, what is the equilibrium shape of this structure, knowing the physical ingredients that are involved. So the first step is naturally to try to identify the physical ingredients that we are speaking about. The first one is going to be important for the whole presentation. It's rotation, the rotation of the planet. I show here a movie where we inject some dye into a rotating tank. And so the basic effect of rotation that you can remember is that it's going to homogenize the flow along the rotation axis. So it's like if everything was constrained along that rotation axis. The second important ingredient is the stratification. The effect of stratification. So here we inject dye in a stratified tank, which is not rotating. Well, the fluid is going to spread horizontally along isodensity surfaces. It's not going to spread vertically. So you can think of rotation and stratification as having kind of opposite effects. Now, if we do the same experiment in a rotating and a stratified flow, well, we're going to form a vortex when we inject this fluid, but it's not going to be able to extend vertically, whereas it would if there was only rotation. So it's going to take kind of a compromise, an ellipsoidal shape, and it's going to stay in that ellipsoidal shape. And the goal is, can we predict that ellipsoidal equilibrium shape? In addition to rotation and stratification, we decided to take into account the effect of the shear, because the vortices are sheared by the zonal winds in Jupiter's atmosphere. So the setup that we are using for this study is going to be a tank, a water tank, filled with water linearly stratified in density using salt. So the water is going to be saltier as we get deeper. We are going to quantify the stratification using the N, which is called the buoyancy frequency, which quantifies basically the density gradient. This tank rotates at a rate omega. F is going to be twice omega. It's called the Coriolis frequency. And we're going to add a shearing device in the tank, which is made of a PVC belt rotating around two vertical cylinders. And we're going to call sigma the shear rate. Then we are going to use a thin capillary tube to inject fluid in the middle of the shearing device. When you inject some fluid in a rotating tank, because of the Coriolis force, basically you're going to generate an anti-cyclonic motion. But as I said before, because we are vertically stratified, this anticyclone is going to be confined vertically in an ellipsoid. Then we're going to want to follow the evolution of the strength and the shape of the anticyclone over time. And to do so, first we're going to put some reflective particles inside of the fluid, and we're going to do what we call particle image velocimetry, PIV. It's simply the fact that we're going to follow the particle's displacement from a top view camera to reconstruct velocity curves inside of the vortex. And on a vertical plane, we're going to follow the evolution of the shape of the vortex by adding a fluorescent dye, which is called rhodamine D, inside of the fluid that we use for the injection. So we can follow the shape, the strength of the vortex, and we're going to complement all of these experiments with direct numerical simulation using an open source solver, which is called Make5. So here you have on the left picture of the principal tank that is used to build the stratification, the salt stratification. And on the right, you have a movie without the shearing device, where you see the horizontal laser sheet. And you can see a very bright spot here, which is in fact the vortex. it's very slow. It's evolving over very long time scales. And it's bright because we added the fluorescent dye inside of the injection. And as I said earlier, we add a shearing device inside of this principal tank to shear the vortex. So the model, now we have all of these like laboratory and numerical measurements. Then we want to confront them with a theoretical model to predict, which can predict the shape of this vortex. I'm not going to go into the details of that model. I just want to give the principal hypotheses and assumptions. Basically, we are going to say that this vortex is in a quasi-static equilibrium, meaning that it evolves very slowly and the shape adapts rapidly. We are going to neglect the diffusion of salt and viscosity. And we are going to say that this vortex is compact. It's a compact vortex, and it's a triaxial ellipsoid. And I'm going to note A, B, and C, the semi-axis of that ellipsoid. Omega C is going to be the vorticity of the vortex. So it's basically the rotation rate of the vortex. And I'm going to denote in the following NCs with stratification inside of the vortex and N outside of the vortex. So skipping a lot of details, if you require the pressure field to be continuous between the vortex and the ambient flow, there is a pressure field in the ambient field because it's a rotating, stratified shear flow. If you require that pressure continuity, you can end up with two laws which allow you to predict what should be the equilibrium shape of that vortex. So on the left, I have written the law which predicts the horizontal ellipticity of the vortex. So beta, it's that parameter. It's basically varies between 0 and 1, and it quantifies the horizontal ellipticity of the vortex. And you can see that it depends, the value of beta will depend on the relative value of the vortex, which is quantified in the Rossby number, relatively to the value of the shear. So it's kind of intuitive. If the shear is very intense, the vortex is going to be very elongated. The second law gives you the vertical aspect ratio of the vortex, C over A, and it depends on the strength of the vortex, again, the Rossby number, and the difference of the stratification between the interior and the outside of the vortex. So these are our two laws, and now the goal is to confront them with our measurements. So here, yeah, because one of them is going to be negative, so it's not physical, so we discard it. So if you look then, yeah, if you have any questions during the talk, feel free to interrupt me. I'm glad to answer during the. So here I represent the horizontal aspect ratio, A over B, for 5 different experiments with increasing shear rate, sigma. And I represent this aspect ratio as a function of, the strength of the vortex, but which you can think as time because the strength of the vortex is decreasing. And the line represents the theoretical prediction. The dots are the direct numerical simulations, and the diamonds are the experimental measurements. So you see a fairly good agreement between the three, the prediction and the measurements. And then most interestingly for us, we can do the same computation using the vertical measurements. So here I plot the measured vertical aspect ratio as a function of the theoretical aspect ratio. So the 1/1 line is going to be the theory. The dots, again, are the DNS. They agree very well with the prediction. And the diamonds are the experiments. We have less measurements because we need to switch between horizontal and laser sheets. So it's kind of not convenient. But you see the prediction gives a good order of magnitude for the experimental vortices too. And the problem in the experiment is that for the prediction, we don't have, for the measurements, we don't know the stratification inside of the vortex over time. So that may explain why we have this discrepancy. Okay, so then the next step is naturally to try to take this theoretical prediction and see what it gives in the case of Jupiter's vortices. So here I applied it to the graduate spots, the oval BA, the oval D, and BC. And using estimates of various parameters of the model for Jupiter, we predict the dashed lines in terms of the horizontal ellipticity of the vortices, whereas the continuous lines shows the measurements the cloud layer. So it means that we predict a consistent shape, or at least on the horizontal direction. In the horizontal direction, we predict the correct ellipticity for all of these vortices using this model. Then, most interestingly, we want to know what this model predicts in the vertical, because we don't have that kind of measurements in the vertical direction. And so if you apply our model, again, this requires estimates of stratification and so on. We find that the great red spot would have a total, so that's the semi-axis. So the total depth of the great red spot would be of about 160 kilometers and about 100 kilometers deep for the other ovals, whereas they are thousands of kilometers wide. So it means that they're really lenticular vortices, really shallow structures, just like the Medes in the ocean. And then the final step is that we can go a little bit further and try to see what we predict for the recent evolution of the great red spot. Because since we observed the great red spot in 1979, we know that it is shrinking in the longitudinal direction, as you can see on these images. And the plot here in the middle represents the decrease of the great red spot horizontal aspect ratio as a function of year, of time. And for each of these dates, we also have velocity measurements of the great red spot. So we can apply our model at each of these dates, taking into account the velocity variations. And the prediction for the aspect ratio that we get are the blue dots on this plot. So it means that knowing how the velocity field evolves inside of the great red spot, we predict the correct trend for its decrease in terms of aspect ratio. And on the vertical direction, interestingly, we find with our model that despite the shrinkage, the depth of the great red spot would not have varied significantly. And I'm going to finish that part by saying that at the end of last year, we finally got some measurements by the Juno mission. So these measurements of the great red spot depth were inversed from gravity measurements, because it is sufficiently big to perturb the gravity measurements, and also using the microwave radiometer on board of the Juno. So basically, I'm not going to get into details, but they estimate that the great red spot is roughly about between 200 and 300 kilometers depth in total. We have a slightly lower value, but that's the good order of magnitude, knowing the uncertainties that we have regarding stratification and stuff like that. And same conclusion for the smaller anticyclones, which are shallower than the great. Okay, so this is all for the first part regarding the Jovian vortices. And so now I'm going to move to the second part. Sorry, I did not understand. Actually, they are very stable, these winds. You mean the change in latitude or the change in... Oh yeah, why the velocities are changing, you mean? That's not understood. It's like, yeah, that's not understood at all. We don't know how to model the fact that the velocities inside of the great red spot are changing. That's not understood at all. So it's like we kind of know the shape, knowing the velocity, but we do not model any, physical processes that lead to that decay. It's just quasi-static equilibrium over time.
Right, and so it's just something that Jupiter does.
We don't really know. So one of my hypotheses is that the great red spot, if you look at it back in the 1979, it had a quiescent core, meaning that there is a ring which is rotating, and inside it's rotating much slower or even quiescent. And as it's shrinking, it's going back to a more classical vortex velocity profile, where the whole vortex is rotating, consistently like a solid body rotation. So one of my guesses is that maybe it was not in a stable, configuration back, and it's just, going towards this new configuration where it's more equilibrated.
And what's the and then in your model, the red spot is due to some sort of density stratification. What's the process that keeps this heterogeneity? Like, what's the red stuff and why is it there?
If I knew that answer, no.
It's all sort of fluidity, right? Where's the bumpiness? Where's the break in symmetry that has it, that has it made out of lighter or dense stuff?
So for anticyclones, basically they are more mixed than their environment. Basically, the environment is stratified, and anticyclone corresponds to a weaker stratification, meaning that it's a mixed region. So one hypothesis is that it's kind of easy to generate anticyclones if you have a phenomena coming whether from deep or above that's going to mix a region at some point, generate a vortex, and then it's going to stay in this compact shape and evolve over time.
It could be impact.
No, it's more seen as, I see it more than coming. One hypothesis is that it could come from the deep convection. You could have a plume impacting the stratification in the atmosphere. This would generate a big anticyclone, and then it could detach, I don't know, and remain in that stratification. But that's very hypothetical, really. Yeah. So for the second part, we're going to forget about those vortices and focus on the zonal winds, so the east-west winds in Jupiter's atmosphere. And again, that work was started before I started my PhD, namely by Simon Caban, and who is now in La Sapienza in Rome, and John Only, who is at UCLA, and of course my PhD supervisors again, Benjamin and Miguel. So again, same process as for the vortices. We try to isolate the ingredients that we need to put in our model to reproduce zonal winds. So for the zonal winds, again, we're going to need the rotation of the planet. So if you remember, it homogenizes the flow vertically if you have only the rotation. So you should picture the zonal winds on Jupiter as extending deep into Jupiter's interior parallel to the rotation axis, up to a depth which has been estimated to be about several thousands of kilometers deep. So they are deep structures contrary to vortices. Second effect that we need besides rotation is the so-called beta effect. So the beta effect is basically a topographic effect. It's due to the fact that if you measure the fluid height parallel to the rotation axis in that shell, the fluid height is going to change with distance to the spin axis. So that's a topographic effect, and you can just picture it as saying, well, if I have a fluid column with a given rotation rate and I move it towards the north or towards the south, I'm going to squeeze it or stretch it, and thereby I'm going to change its rotation rate. So that's the beta effect, and you can express the beta parameter as a derivative of the fluid height. This effect is really important regarding the formation of zonal flows, and I want to show you that by showing two simulations of turbulence, bidimensional turbulence, without and with the beta effect. And so what you can see on these simulations, just very qualitatively, is that if you have no beta effect, you're going to end up with a rather isotropic system, whereas if you add a beta effect along the north-south direction, you're going to have some zonation in the east-west direction that develops. And this exactly corresponds to the zonal flows that we see on Jupiter. And finally, we need some forcing, which is going to inject energy into the flow. So on the planet, on Jupiter, it's still very much debated what forces the zonal jets. It can be moist convection in the weather layer. It can be baroclinic instabilities. It can be convection at depth, the one I mentioned for the red spot. So all sorts of planetary processes. And of course, experimentally, we're going to simplify that very much. So having these three physical effects in mind, we built the following experimental setup. So we are going to use a cylindrical tank, which is, again, a plexiglass tank, 1 meter in diameter, 1.6 meter high. We fill it with about 600 liters of water. And we are going to impose a rotation of 75 rotations per minute. So it means more than a rotation per second. It's a fast rotation for that size, that container size. And it means that because of rotation, the fluid free surface is going to be paraboloidal because of the centrifugal force. And so we are going to naturally have a beta effect because the fluid height increases with distance to the axis. And finally, so rotation, beta effect. And finally, we're going to perform a forcing in the tank by circulating the tank's water through a bottom plate, which is drilled with 128 inlets and outlets distributed on that polar lattice. So we have submersible pumps, which are placed beneath the plate, and we circulate continuously the tank's water through that plate and through that inlets and outlets. And the important point is that if you have as much inlets as outlets on each polar ring, so if you zonally average this forcing, it is zero by construction, meaning we do not directly force any zonal circulation. We just let it develop by itself. So in terms of visualization, we again use PIV, particle image velocimetry. So we put some fluorescent particles inside of the water. We generate a horizontal laser sheet, and we use a top view camera to record the particles motion. So here you have a picture of the experiment at rest. So all the instruments, the computers, the camera are at the top. You have the deep fluid layer here. You can guess the bottom plate inside and the laser on the side. Here you have a zoom on the bottom plate where you can guess maybe the inlets and outlets. And if you turn it upside down, you see the submersible pumps, very small pumps that are used to generate this forcing. And here on the left, it's a video of the experiment. Yes, noise, but that's the noise I hear here. So that's the experiment once it's solid body rotation. So you can see the very deep crystal phase that develops because of the fast. Okay, so now let's take a look at some visualization of the flow, of the corresponding flow. So here I'm going to show a movie of, as seen from the top view camera, a movie of the particles, 15 minutes after the forcing has been turned down in the experiment, and it's accelerated 40 times compared to real time. So you can see on this movie that you can get some zonal circulation developing in the experimental domain, whether in the clockwise direction or in the anti-clockwise direction. So we are indeed able to reproduce the spontaneous emergence of some zonal motions in that experimental setting. And the surprise that we had is that, in fact, we identified different regimes of zonal circulation. So to illustrate these two regimes, I'm going to show two movies of the azimuthal component of the velocity for two different forcing amplitudes. So the color basically represents whether clockwise or anti-clockwise. So this movie corresponds to the first regime that we identified. You see that there is a fast development of about 5 to 6 prograde and retrograde jets in the system. And if I do now another experiment at a much higher forcing amplitude, we obtain the following flow, where you see that we start in this regime, and after some time, the jets migrate, merge, and you have this completely new statistically steady state where you have only 2 to 3 prograde jets left, which are broader and which are much more intense. Okay? So that's really, these are really two different dynamical regimes. So I just wanted here to illustrate these two regimes using space-time diagrams. So here I plot the zonal flow profile as a function of time for an experiment in regime 1. So you see the very steady jets. And the same visualization for regime 2, where you see the transient. You start from regime 1, there is a quite long transient. This is in rotation time units. And the new statistically steady state that is obtained at the end. And so our guess is that this second regime is the one which is relevant to gas giant application, where the jets are very strong and contain most of the kinetic energy of the fluid. So from the fluid dynamics point of view, we wanted, of course, to understand why we have these two regimes and what is the transition between the two regimes due to. So we perform what we call the hysteresis experiment. So this means that for a given experiment, you can change the forcing amplitude step by step in the same experiment and measure the corresponding zonal flow at each time step. So I did so by increasing the forcing. So you see the transition between regime 1 and 2, which occurs at this forcing intensity. Then I did the same measurements where I decreased the forcing amplitude step by step. And you see again a transition between regime 2 and 1, but it occurs at a smaller forcing amplitude. So physically, this is very interesting because it means that there is an area here, which is shaded, where you can obtain for the same forcing amplitude, you can obtain whether regime 1 or regime 2, depending on the history of your system. And so this means that you have some bistability, you can have two stable states, and hysteresis associated with this bistability. So then next step was to model physically this type of transition. I'm not going to go again in the details of the model. Just keep in mind that it's a bidimensional simplified model of the experiment. The important point is first to understand what happens in regime 1. So in regime 1, the process is that if you look at what happens just above, locally above a given forcing ring, what happens is that, so these are azimuthal and radial components of the velocity at the very beginning of an experiment, just above the forcing ring. And what happens is that each forcing ring is going to radiate some Rossby waves. So these Rossby waves are responsible for this kind of pattern oriented towards the left that you see in these maps. So this would be the west and this would be the east, and Rossby waves propagate towards the west. So one important consequence is that when you radiate some Rossby waves, because they propagate towards the west, they are going to dissipate away from the forcing region, and they are going to deposit some angular momentum going towards the west. This means that you're going to generate a retrograde flow far from the forcing region, and you're going to accelerate a prograde flow at the forcing location because of angular momentum acceleration. So that's the basic picture. And so if we go back to the global scale, what it means is that each forcing ring is going to radiate Rossby waves. This is going to generate a prograde jet above each forcing ring and a retrograde flow in between. So that's regime 1. Now, the question is, why do we switch to a second regime? I'm just going to give a brief, simplified explanation. It's the fact that if you add a background zonal flow behind these waves, you can have a feedback of the zonal flow on the waves, and then you can have a linear resonance of the Rossby waves. So I'm just going to explain it just qualitatively. Here I represent the acceleration of the zonal flow by the waves as a function of the zonal flow velocity. So what happens is that if you have no zonal flow initially, the waves are going to propagate towards the west, because the waves are going to propagate towards the west. If you add a zonal flow which has the exact same speed as that westward propagation, then the waves are simply going to become stationary. They're going to phase lock with the forcing, and they are going to be able to amplify through time because they are phase locked with the force. So that's why you have this peak when U, the zonal flow, is equal to minus C, the phase speed of the Rossby. So that's a very simple linear resonance. That's a Lorentzian curve. Linear resonance, okay. And then just to briefly explain, with this type of non-linear behavior between the acceleration of the zonal flow and the zonal flow itself, you can explain why you have bistability, multiple regimes. So let's just imagine that this yellow curve here is a term that accelerates the zonal flow. Okay, it's the R of U. But the zonal flow is also damped by some physical processes, which in our case is due to friction at the bottom of the tank. You can model this friction with rotation by basically a linear damping of the zonal flow. And so the zonal flow, you're going to find a steady solution when the forcing, the acceleration of the zonal flow, which is the yellow curve, is equal to the damping of the zonal flow. That's where you're going to have a steady state. And so given that resonance curve, you can see on that specific example that, well, you have three intersection points, so three possible stationary solutions. One of the three is unstable, it's not stable, unstable equilibrium, and the two others are stable solutions. U1 will correspond to the regime 1. It's a low amplitude stationary solution, which is sub-resonant, whereas U2 would correspond to the second regime. Okay? So this resonance explains why you can have this solution. Skip that and just say that the conclusion is that the transition that we see is due to resonance between the Rossby wave and the zonal. And so if we want to go back to the planetary application, here I just wanted to give some very basic velocity comparisons to see what it could imply at the planetary scale. So basically what I'm going to do is to look at the propagation of the Rossby wave once they are advected by the zonal flow. So if we are in the configuration U1, the zonal flow is low, so the Rossby waves still propagate westward. We are sub-resonant. If we are in the configuration in regime 2, the zonal flow is sufficiently fast such that the waves propagate eastward. So we will be in regime 2, super-resonant. So we can take a look at Rossby waves propagation in various flows. And so I found this map of the Rossby wave phase speed once advected by the zonal flow in the Earth oceans. And you can see that it is negative in most of the ocean, meaning that we would deal with regime 1, the sub-resonant flow. However, maybe for the strong Antarctic circumpolar currents here, it could be the Rossby waves are propagating eastward, meaning that it could be a super-resonant regime 2. Then for Jupiter and Saturn, so it's kind of tricky to find Rossby waves data for these planets. I found estimates at 7 degrees north on Jupiter and 42 degrees north on Saturn, where you can basically follow features that you see in the clouds to try to interpret them as Rossby waves and estimate their velocity, their propagation velocity. So for Jupiter and Saturn, using the hotspots displacement and the north ribbon displacement, these papers by Arrighi and Gunnarsson shows that they could correspond to Rossby waves propagating eastward, meaning that in both cases, we would be in regime 2 with super-resonant jets on the gas giant. Of course, these are very simple velocity comparisons, and one big question that needs to be addressed is how is the forcing of the waves influencing the resonance mechanism that we're seeing, because the forcing is totally different in our experiment and in these planetary fluid. Okay, I'm a little bit short on time. So I'm going to finish this talk by introducing you to my postdoctoral project here with Krista. And so the idea is that for this postdoctoral project, so it's in collaboration with Krista and also Carver Bjergson, who is at Arizona State University. And the idea is that we're going to leave Jupiter's atmosphere, but we're going to remain in the Jovian system. We're going to focus on Europa, which is an icy moon of Jupiter, which you can see here on this nice picture of the Cassini spacecraft. And so Europa is a moderate, it's a moon which has roughly the size of our moon, about 3,000 kilometers in diameter. So of course, compared to the features I just described, it looks very small. It's very bright because it is covered with an ice layer, an ice crust. However, as I said earlier, we know that from the induced magnetic field that we measure around Europa, we know that there is a salty ocean circulating below the ice crust of Europa. And so from the fluid mechanics point of view, the questions that we want to address is what drives the flow in this ocean? What does the circulation look like? And how is the circulation transporting heat and materials from the mantle to the ice and vice versa? So the goal, is to understand the global geophysical evolution of that kind of process. So as I said in the introduction, in my postdoc, here the approach is different, we're going to perform some global scale modeling. So these two approaches of the three of them are really complementary because, for instance, with global scale modeling, what we can do that we cannot do with that approach is that we can reproduce the actual geometry of the planet or the satellite. We can reproduce the spherical geometry. And that's very important if you want to draw conclusions for the planets. So that's the first point. So we're going to have naturally detailed effects because of that geometry. And the second point is that we can easily introduce some thermal forcing, which is more realistic than the mechanical forcing that I presented earlier. So there are pros and cons for both methods, but they're really complementary. I think I'm going to go, I'm going to accelerate because I don't want that seminar to last an hour. So I'm just, very simply the model, the numerical model that we use, we're going to say that Europa's ocean can be modeled as a fluid layer, which is contained in a spherical shell. So of thickness d. And the flow inside, so this shell rotates at a rate omega, and the flow inside of the ocean are going to be driven by a temperature difference between the bottom and the top of the ocean. The bottom is hotter than the top. For the planets, this corresponds to the fact that the mantle of Europa is heated by radiogenic heating and also thermal, also tidal heating. So this heat is forcing convection motion in the ocean. The results when you heat a fluid from below and cool it at the top is that you're going to generate what we call thermal convection in the system, where you will have hot plumes going up and cold plumes going down, and the system is going to be very dynamic. Okay? That's the thermal convection that is going to take. I presented here the equations. I'm not going to go through them. I just want to, so it's just the governing equations of the system. So momentum equation and heat conservation equation. And I just wanted to stress out that the solutions of these equations depend on three key non-dimensional parameters: the Ekman number, which compares the viscosity to rotation; the Prandtl number, which compares the viscous to thermal diffusion; and the Rayleigh number, which basically compares the driving force, the buoyancy, to the diffusion. So the key points that I want to underline is that depending on the value of these three parameters, we're going to end up with different circulations inside of the new structure. So I took this regime diagram from Krista's paper of 2019, where she shows the Rayleigh number as a function of the Ekman number. And my key message here is that, so very simply, this gray area is an area where the forcing is not high enough. So basically the fluid is stable, whereas above here it is unstable. And the colors just represent different regimes of convection. And Krista estimated, using parameters estimate for Europa, that Europa should lie about here in this regime diagram. My key message here is that these values for the Ekman number and the Rayleigh number are completely out of reach of current numerical capabilities, and even experimental. It's impossible to reach that kind of regimes. But what we do is that we're going to do a simulation which is at a very much moderate Ekman and Rayleigh number, but we pay attention to the fact that we know in which regime Europa is the, let's call it the red regime. It's not a big deal what it corresponds to. So we want to be in the same regime as Europa, even if we are working at a smaller Ekman. Okay, that's the best we can do basically with current capabilities. And so Krista shows, using these parameters for Europa, that you have a very interesting circulation in the ocean. Here she shows a snapshot of the zonal flow and the radial flow at mid-depth in the ocean. And basically you have a strong retrograde zonal flow at the equator. And in the radial direction, you have a very strong upwelling occurring at the equator of the ocean. And that's very interesting because it means, just thinking about heat transfer and material transfer, it means that, well, the transfer between the ocean and the ice is going to be very inhomogeneous in the ocean when you compare the poles versus the equator. And so it's going to have huge implications regarding the exchange with the ice. So that's the big picture of Krista's work. And my postdoctoral project is to ask the question, well, these circulations correspond to simulation where you impose a homogeneous temperature at the bottom of the ocean. So you heat the ocean uniformly. And we know that if Europa's mantle is heated by tidal heating, by the tides, the deformation of the mantle, basically, we know that the heating of the mantle is going to be very heterogeneous. So here you have a map of the heat flux that you expect at the top of the mantle, which was derived by Carver-Pearson. And you can see that the heat flux has very strong variations of order 1, so that they should need to be taken into account, with hot poles, colder equator, and a non-negligible longitudinal variation along the equator. So the heat flux coming from the mantle is supposedly very inhomogeneous, and I want to address the question whether is this mantle pattern reflected at the ice-ocean boundary, or is it going to be just erased by the vigorous convection into the ocean, which is going to mix everything together and will not have any imprint of that tidal pattern at the top of the ocean? I think I'm just going to give the big picture of where we're at, because it's already been a long time. So I just want to say that basically my approach is to start from the homogeneous case and try various forcing patterns, inhomogeneous forcing patterns, including the tidal one. And in a nutshell, I'm going to skip all that. I'm just going to go to the big picture message. In a nutshell, what we find is that if you impose a homogeneous heating case, that's Krista's result. You're going to have a strong upwelling at the equator. And from the thermal point of view, it's going to mean that the equator is going to be hotter below the ice than the poles. So you're going to have more important heat flux at the equator than at the poles. Whereas if we impose a tidal heating pattern, we find that you have a very different circulation that occurs in the ocean. And the result in terms of thermal exchange and heat flux is that the poles in particular are going to be this time hotter than the equator. So you're going to have a greater heat flux at the equator to the ice shell. And you still see very strong longitudinal variation. So this has possibly, this means that taking into account the tidal heating is likely to have a strong influence on the convection and so on the heat transfer and on the natural exchange. But these are preliminary results, of course. So to wrap up very rapidly, so we talked about Jupiter. I showed you a study about Jupiter's anticyclones and the fact that there are shallow structures, lenticular vortices contained in the weather layer of Jupiter. I present you an experimental setup where we can reach very strong zonal jets in an experiment, and that we show evidence of the key role played by Rossby waves on the development of the zonal flow. And finally, of course, my postdoctoral project with Krista, we have a lot of ongoing work. And so here I focus on Europa, but the goal is to have generic conclusions for other icy moons, such as Titan and Enceladus, and to also investigate other heat flux patterns different than the tidal heating pattern. Thank you very much. Stop here.
Thanks, Daphne, for a great talk.
So in the last preliminary results, it looked like the longitudinal tidal variations that seemed sort of a second order to the latitudinal variations in heating were completely overwhelming the response. In the sense that, when you, so the mean bottom temperature, right? That's what you impose.
Yes, this is imposed.
Right,
Yeah.
and so if you take out the longitudinal pattern, you have a strong response, right? But then, like, you put in these subtle variations, or, okay,
So yeah, just to make it clear, for instance, if I impose only the
Right.
latitudinal pattern, what you get is that you still get the same zonal and radial flow than the homogeneous case, except that since you're forcing the pole stronger, you will have a stronger stronger convection, and hence stronger heat transport at the poles.
Yeah.
That's the latitudinal effect of the tidal heating. And the longitudinal effect of the tidal heating is very interesting because it drives a completely different circulation, including the fact that because you have longitudinal variations at the equator, longitudinal temperature gradients, you're going to drive a baroclinic circulation, like a thermal wind, basically, with so this very specific zonal flow pattern associated with radial downwelling and upwelling at the equator.
And so when you put them together again, it seems like this thing wins.
When you put them together, you have the baroclinic circulation. Yes, we don't have the zonal flow anymore, but for the heat transport, it's mainly the radial circulation that is
Okay.
important. So that's
Okay.
why
Yeah.
even if this wins, I mean, zonally speaking, the poles are still going to get probably higher heat flux at the poles than at the equator.
Gotcha.
So I think it was on one of the like ongoing or future work slides, but looking at the temperature on the mean top temperature below the ice, is there like collected data for ice thickness on Europa, or is that something that we're trying to figure out as well?
So on Europa, Krista is going to correct me if I'm wrong because I'm new to the icy world, so I may say wrong stuff. But I think on Europa, we don't have ice thickness measurements. Seems to confirm. We have for Titan and Enceladus. Okay. So we could try to work on that, but probably with the Europa paper mission, and we're going to have much more constraints on the ice flow thickness on Europa. But so yeah, one interesting point is that from the heat flux maps that we can build below the ice, we can of course try to infer the ice show range.
About the second laboratory project, I wonder if you could talk a little bit more what organizes the structures in that regime 2. You sort of commented on this briefly. And so it seemed like in regime 1, they were symmetric in terms of flowing to the left and right and set by your forcing.
Yeah.
But then you went to a different length scale. And so my question is, can you guess what controls that length scale? Is it sort of halfway between dynamically controlled and controlled by the forcing, or is it entirely controlled dynamically? And it also seemed that maybe this is just because of the geometry, that there was like localization. So there was like fast flow in a thin layer that was balanced by wider layers going the other way, rather than having symmetry, or did it just look like that? Right, so when, maybe the next one, just
What I didn't
Yeah.
understand, I understood
So-
your first question.
so
comment, but the
when I
second one-
look at reds and blues on the left, they're controlled by your forcing,
Yes,
but
yeah.
it also maybe not quite. In some of the figures, it looked like flow was going one way then the other way in a fairly symmetric pattern. Whereas here, you're now going to see this focusing of really dark reds, meaning fast flow one way, and wider regions that go the
Yeah.
other way. Is that actually happening,
see.
or is it just maybe just misleading? I mean, now it seems like there's a strong blue ring and a strong red ring, but in
Yeah.
some of the other plots, maybe just because of projection, it was like, there must be some conservation. Yeah, here, right? So I'm like, okay, there's some conservation principle going on.
Yeah.
Mass for sure, right? Angular momentum probably too, but it seemed like you had weak flow one way and stronger flow in the thinner layer the other way.
Yeah. So that's, you're right on all of these points. Like, so for your first question, for the scale of the jets, in the second regime, it's probably a mixture between the scale which is set because it's still interacting with our forcing strongly, but also we argue that we're switching to a regime where the jets equilibrate at their natural scale without being influenced by the forcing too much. Usually that scale, that dynamical scale, is quantified as being the Rhine scale, which is basically the only scale that you can deal with the velocity and the beta effect. So it's square root of u over beta. that suppose that you really have a scale decoupling between the forcing and the scale of the jets, which is in between. Yeah, it may be the case here, but we're not 100% sure. Plus, there is the fact that we're confined in the experiment, and we are going to have finite side effect that impede the jets from finding their natural density. But we think it's close to that. And for the second question, yeah, you don't have a symmetry between the prograde and the retrograde fluid. So typically, the prograde, you can understand that as potential vorticity mixing. I don't know if you're familiar with potential vorticity. It's basically vorticity, local vorticity plus planetary vorticity. And it's a quantity that is materially conserved in the fluid. And so the prograde jet corresponds to the retrograde flow corresponds to areas where this quantity, the PV, is well mixed. And this leads to broad retrograde flow. Whereas the prograde jets corresponds to sharp gradients between well-mixed zones of PV, and this corresponds to very sharp prograde jets. So the zonal, the prograde jets are very sharp and thinner than the retrograde flow, which is broader. And yeah, and this is also due to the effect and to the fact that the jets can become unstable. But yeah, there is no symmetry, at least in the second regime. There shouldn't be a symmetry between the prograde and the retrograde flow.
One last question.
Do you think doing floating different elevation in your second experiment would matter? I mean, it could be like forcing constant through the color.
Yeah, so we assume that because we're really rotationally constrained, everything is going to be basically homogeneous along the rotation axis. So even if you were to do the EIV at different levels, we assume that you would see the same thing. We didn't verify it experimentally, but Benjamin, one of my supervisors, did a direct numerical simulation, one direct numerical simulation of the experiment, because it's extremely costly. And you can tell, I don't think I have the slide there, but you can tell that the flow is really kind of homogeneous vertically. So it doesn't change a lot.
Okay. With that, let's thank Daphne for a great talk. For those interested, we'll be going out for lunch afterwards. Part of the seminar goes here at 11:45 if you'd like to